good afternoon. I was waiting a few more minutes that more of the students can join today. I will also welcome Georg Fuchsbauer from TU Wien in regards to his presentation today about space-efficient blockchain. And so I will give to you, Georg, and thanks for your presentation.
Can you hear me all right?
Yeah, but not that good.
Okay. Better now? I guess the office is very empty. Can you see the shared slides?
Yeah, we can see the slides.
Okay, then I'll just start. Yeah, thanks for the introduction, the invitation to give this talk. I will talk about space-efficient blockchains, and it's basically about the problem that today's blockchain systems rely on the fact that all data that was ever uploaded to the blockchain will stay there forever, and this data should be stored at many decentralized places, which creates a lot of storage overhead, and I'll talk about two approaches how we can do better. Excuse my voice. Okay, let's start at the beginning. Bitcoin was introduced by an anonymous author going by the name of Satoshi Nakamoto, and it's arguably the most successful ever deployed digital currency, and the revolutionary idea was that it's decentralized. So there's no central banks emitting digital coins, but everything is decentralized, including the creations of coins. It has hard-coded inflation, so there's a maximum number of bitcoins that will ever exist, which arguably has contributed to its success in times of quantitative easing. Moreover, it's pseudonymous, so there are no concept of real identities on the blockchain, which arguably has contributed to its bad reputation, at least for a long time. How does Bitcoin achieve this? So it maintains a public history of all transactions that have ever happened, and that guarantees consistency because everyone can verify that everything was done correctly. And it then uses a distributed consensus protocol to extend the history. So if you want to, say, do a very primitive currency system and you have some authority that everyone trusts and privacy is not an issue, then the following would be a very simple solution. So the authority publishes the so-called ledger, which is just a list of all account balances. And then when someone wants to transfer money, say Alice wants to transfer her 1 unit that she owns according to the ledger to Bob, then she contacts the authority, says, now Bob owns 1 more because I transferred to him, and the authority publishes a new snapshot. That's actually not how Bitcoin works, because in Bitcoin there's no notion of accounts, but basically only transactions are recorded. So if Alice at some point got this 1 coin from Charlie, then she makes a new transaction transferring it to Bob by basically referring to the old transaction when she got the money and now spends the output of this previous transaction. So in Bitcoin there's no notions of accounts, but only transactions. But then if you go through all the transactions, you can deduce which account has how much money. Okay, how can Alice identify if there's no authority that checks who she is? We use digital signatures for that. And so every coin is associated with a signature public key PK. And so Alice owns a coin if the coin is associated to a public key and she knows the secret key that goes with it. And so if she wants to transfer this money to Bob, then Bob creates his own verification key, in Bitcoin called an address. And yes, I'm oversimplifying a bit for the sake of not complicating things too much. And when Alice wants to transfer her Bitcoin to Bob, then she signs using her secret key this transaction and adds it to the ledger. So this is called transaction. So what happens if Alice does not only send her coin to Bob, but also to Charlie, which in digital currencies is usually a big problem called double spending? That's actually not a problem if you have a public ledger, because the rule is that Alice can only spend coins that she received at some point, so there must be a transaction giving value to PKA, and no transaction has spent it yet. So whatever transaction she does first will be accepted, and every other transaction trying to respend will be rejected. Okay, now the question is, that's nice if we have such a trusted authority, but how can we eliminate it? So how can we make sure that the validities of transactions are checked, and then new transactions are published and everyone agrees on what these transactions are? So for this, Bitcoin introduced the concept of the blockchain, where every block is basically a set of transactions, and then these blocks are linked together using hash values. So how this is actually done is not part of this talk, so you need to find ways to incentivize people to participate and try to create new blocks. You need some protocols to decide who gets to create new blocks, and yeah, that's done using consensus mechanisms. And there was a lecture in this lecture series on this by Krzysztof Pieczak, who looked at the sustainability questions that arise from consensus protocols. But in a nutshell, what's done is that miners are paid to do this work of verifying and publishing new blocks. So basically in Bitcoin you have this components that depend on each other in a circular way. So we saw that if you had a trusted ledger, then you could create a payment system. If you have a payment system where you can create new money, then you can actually reward miners by giving them the money that's created in every new block. And if you have a consensus that basically emulates this trusted party, then you have a trusted ledger. So you have this cycle of self-enforcing things. Okay, so to look at the problem of this ever-growing transaction history, let's look at how these transactions actually work. So assume that Alice at some point got 6 Bitcoins. It's associated to her public key, so she can now transfer the 6 Bitcoins to Bob by signing this transaction. So what if Alice did never receive a payment of 6 Bitcoins, but say she got 2 Bitcoins and 2 Bitcoins at some point and then 3 Bitcoins later? Then luckily the transaction can have many inputs, so she can input all of this using for every transaction, for every input, a signature that signs the transaction. And now, of course, she does not want to spend 7 Bitcoins to pay Bob 6 Bitcoins, because that's now, depending which day you look at, but around $90,000 difference for her. So what she can do is she can just add another output and send back 1 Bitcoin to herself, called the change of this Bitcoin. What's actually being done is that she will not basically take all the change, but leave a little bit for the miners, because otherwise there's no incentive for miners to include the transaction in their block. Good, so she broadcasts this transaction. It's picked up by the miners, it's put in a block, and this block is then published, and it's decided by whatever consensus mechanism you use, which block is accepted by everyone. Good, so once this transaction is there, so Bob now owns this 6 Bitcoins coming out of that transaction, and so he can now make a new transaction, spending these 6 Bitcoins and say transferring 2 to Charlie and keeping 4 for himself. So what this transaction now does is refer back to the output of an existing transaction in the system and spend that. And Bob broadcasts this transaction, it's picked up by a miner, put into a block, and now Charlie owns these 2 Bitcoins coming out here. So every input of a transaction in a block in Bitcoin basically refers to a previous output of a transaction that is being spent. And so, of course, you might wonder, where does the money come from? Well, it goes back to these coin-based transactions, which is just by definition some money that is created with every new block, which is currently 3 1/8 Bitcoin per block, and by definition goes to the miner. Good, so basically if you look at all the transactions and all their outputs, there's 2 types, either they're spent or not, and those that have never been spent, so no input or no transaction refers to them, they are called the unspent transaction outputs, or UTXO in Bitcoin lingo, and they represent the existing money in the system. So what does it mean to own an output, to own Bitcoin? It means that it's an output that hasn't been spent yet, which, as we said, is associated to a public key. And if you know the secret key, then you can spend it. How do you do this? You create a transaction, refer to the output, and now add a signature sigma under that public key on this new transaction, and that authorizes the spending of the previous output, and only you who knows the secret key can do so. So signatures guarantee that no one can steal your Bitcoins. So that's one property we want, no one can steal money. Another property, which might be less obvious, is that we don't want anyone to create new money out of thin air in the system, apart from this defined coin-based transactions. And so we want a transaction to be balanced. So we want the outputs to be not more in value than the inputs. And that's also something that you can just check by looking at it, and no miner will ever accept a transaction that creates more output than went in. So here it seems obvious, but we'll come back to this notion of balancedness later again. So what are the drawbacks? In terms of scalability, well, first of all, there's weak anonymity, because if for some reason network analysis or whatever, you know who owns this some transaction output, then you know exactly when this output is spent. And there's now companies that analyze the Bitcoin blockchain, building transaction graphs and helping, for example, law enforcement agencies to trace payments. But that's not the topic of this talk. The drawback that we want to look at is bad scalability, coming from the fact that if you want the blockchain to be publicly verifiable, then you have to keep all data in the system forever. So if you want to know whether this transaction was legitimate, whether Charlie really owns these 2 Bitcoins, you need to be sure that these 6 Bitcoins were spent legitimately. So you need to check this signature. And again, you need to know whether, who was it? Alice got these 6 Bitcoins legitimately. So you need to check all signatures in the system. That's a problem because the blockchain keeps growing and growing. And so for Bitcoin, for example, it is now over 600 gigabytes. If you look at the second most valuable blockchain, Ethereum, there it's even worse because there's even more data. So why is this a problem? Because if you want to contribute to the system and, for example, mine, or not rely on anyone else telling you something about the blockchain, then what you should do is download the whole blockchain and verify it, which will run probably several days if you did it on your laptop. Once you've done it, what you could do is actually just store the unspent, if everything's valid, store the unspent transaction outputs, because if you now see new transactions, you can check whether they are legitimate or not. So this data, this unspent transaction output, is actually a lot smaller. So in Bitcoin, it's 11 gigabyte, and as you can see in this graph, it can also decrease if more transactions or more outputs are spent than new ones are created. However, if someone tells you this UTXO set, then you cannot, you have to trust that someone, because they could tell you whatever. So what would be nice is if we had a blockchain where you can just forget about all the unspent transaction outputs, because they can't be spent anymore, but still maintain public verifiability. So something like, if you look at this path that some coin might take, so it's output here, and then it's input to a new transaction, and then it's spent again, then wouldn't it be nice to just forget about this middle transaction here and say the money came from the previous transaction and ultimately from a Coinbase transaction. So that's an idea that had been around, and it's called cut-through, because you can cut through these transactions. If you look at Bitcoin, you cannot do that, because if you get rid of this transaction, then basically you break the path of verifiable signatures, because you need sigma prime the signature here to check whether this output here was spent legitimately. For this dream of doing cut-through, allowing information in the blockchain to just be discarded without hurting public verifiability is exactly what Mimblewimble, a cryptocurrency scheme that I'll present next, achieves. So as has proved good practice with new cryptocurrency technology, it was proposed by an anonymous author, this time by someone calling themselves Tom Elvis Jedusor, which is the name of this Harry Potter character Voldemort in the French translation. And so this was really just a very short text file that they posted, where they sketch the main ideas, some of which had been around before, most of them invented by Gregory Maxwell, and these ideas were then picked up by and further developed by Andrew Poelstra. So what I guess the main motivation of the this anonymous author was a cryptocurrency scheme with improved privacy, because in Mimblewimble all the amounts that are transacted are hidden, and also the input-output relation are blurred. And if you look at the file, you can actually see this motivation, because they write things like about companies whose business model is to monitor and control the lower classes. What I find a lot more interesting about Mimblewimble is the scalability aspect, because it allows us to forget about spent transactions. So with my first PhD student back in Paris, Michele Leroux, and Yannick Zora, who now works for Ledger, the crypto hardware company, we formally analyzed this proposal, and we showed that yes, this is actually secure. So let's look at the ideas. So let's look at what kind of anonymity you can achieve by starting from Bitcoin. So one thing that Bitcoin already gives you is that within a transaction, there's no notion of which output comes from which input, right? So this 3 Bitcoins being the first output could be either come from the first and the third output, or from the second output. There's no notion of such a thing. So this gave rise to this idea of coin join, meaning that what if you have several transactions, can't you just put them together so that you just have a lot of inputs and outputs and you don't know what corresponds to what? That's something that in Bitcoin you can actually not do, because every input is associated with a signature on the transaction. So you can't glue things together. I mean, you can, but you would still see which signature signs what and which transaction input and outputs go together. What you can do in Bitcoin is you can do this interactively, right? If you have a lot of users that have transactions, then before posting them, they could just get together, merge all of it together, everyone signs the overall transaction, and that way you could get blur the path of inputs and outputs. But this has to be done interactively. And so what Mimblewimble allows you to do, as we'll see, is you can do this after the transactions have been posted. Another idea that it uses is about hiding amounts. So that was something that had been proposed before in what's now called confidential transactions, also by Maxwell, where the idea is that you don't give the amounts of the inputs and outputs in the clear, but you sort of encrypt them. That's something that's not compatible with Bitcoin, but it has been used by other cryptocurrencies, most notably Monero, which is the largest of these so-called privacy coins that allow you to make things more anonymous, as with Bitcoins. Of course, adding to bad reputation. The main issue with this is that now balancedness is not obvious anymore, right? Because if all the amounts are encrypted, then what guarantees that you didn't put a lot more money coming out of a transaction than went in? So I'll quickly show you how this is addressed in confidential transactions. So this is the one technical slide where I introduce Pedersen commitments, where think of it just as some sort of encryption. So it uses discrete logarithm hard group, which is usually instantiated using elliptic curves. So if you've heard of elliptic curve cryptography, that's exactly what that's about. So in this group, we have one element called the generator, which if you denote the group additively, you can think of it as being the 1 in integers. And now what does discrete log hard mean is that if I give you x times g, where x times g just means g added to itself x times, for some random number x, then it's hard to find x. And if this group was a finite multiplicative group, then that would actually be the discrete logarithm, literally. Okay, what's a Pedersen commitment? So we have two parameters, which is just two generators of this group, two elements g and h. And if you want to commit to some integer b, think of it as encrypting, you pick some random value r, and you define the commitment to v using randomness r as v times this first generator plus r times the second generator. And if you've seen a little bit of cryptography, then this is basically like the one-time pad in this discrete log hard group, because this value r completely masks the value v, and so a commitment to value v completely hides the value that you committed to. What's particularly useful about these Pedersen commitments is that they are homomorphic. So what does that mean? It means that if you have two commitments, one to v1, one to v2, with randomness r1, r2, then if you just write out the definition and you regroup, you see that that's the same as a commitment to the sum of the values using the randomness. That's the sum of the individual randomness. So to illustrate this, if you have a commitment to the value 1 plus a commitment to the value, another commitment to the value 1, you subtract the commitment to the value 2. This will be a commitment to 1 plus 1 minus 2 equals 0. And if now you also choose the randomness so that 5 plus 10 minus 15 equals 0, then you actually end up with the 0 element in this group. And so hopefully that already gives you a hint to how you can achieve showing balancedness of a transaction. So here's what confidential transaction does. So instead of putting the payment amounts in the clear, everything is committed. So everything is this group element computed as the value times h plus the some randomness times g. And how do you ensure that transactions do not create money? This balancedness feature, you check whether the sum of the outputs minus the sum of the inputs equals 0. Because if you just write this out, right, if you write out the sum of all the output commitments minus the sum of the input commitments, you get that that's a commitment to the sum of the output values minus the sum of the input values using this compound randomness. And so if the transaction is balanced, then this value here is 0, right? That's exactly sum of the outputs minus sum of the inputs. And if you set up the randomness in this way so they cancel out too, then everyone can just check whether that is 0. So under the discrete logarithm assumption, this is actually means that this transaction is balanced. Okay, now that's nice if you want privacy, but you don't solve any scalability, right? Because you still have these signatures in the transaction, and so you can't do a non-attractive coin join. You can't take two transactions and glue them together, because every signature would still be on the original transactions. You can't do cut-through because you need to keep all the signatures to verify the flow of all the money in the system. So enter Jeluser, who says this is all well and good, but what about we don't use any more signatures? And since we don't use any more signatures, we also need these public keys. So a transaction would now only be committed input values and committed output values. So now the question is, what does it even mean to earn an output if there's no public key associated with it, if there's no secret that you can require to spend the output? So what he says is, well, the secret key of this output here, remember the output is such a commitment, is this randomness R that was chosen when the commitment was created. So that's the secret key that makes you own this coin. Of course, now there's a problem, right? If you want to show balancedness this way, then the sender has to arrange this randomness so that it cancels out. And so in the extreme case of there only being one input and one output, these two commitments would have to be the same so that they cancel out. And so the sender who chose the randomness of the input commitment would now also know the randomness of the output commitment. So the receiver of the payment is not the only one who can spend it. So by definition, he or she didn't receive anything because the sender still owns it. So how can we solve this? Well, we can just, that's what Jeluser proposes, everyone chooses all independent randomness, right? So only you who created this output when you received the payment will know your secret key. The problem now, of course, is if we use this equation for well-balancedness, then yes, the values will cancel out if it was done correctly, right, if it's balanced. But these randomness values won't cancel out. So instead of the old equation, we would get that the sum of the outputs minus the sum of the inputs is 0 times h plus x times g. So it's basically a commitment to the value 0. So what can we do? We can just prove that sum of the outputs minus sum of the inputs is a commitment to 0, and then by definition, that means that the transaction is well balanced. So how this is done is actually using a Schnorr signature because it's a proof of knowledge of its secret key, but basically you could view this value x times g derived as sum of outputs minus sum of the inputs as a signature public key, and then you sign under this secret key. So that was me when I first saw that, because it's all well and good that this signature will prove that the transaction is well balanced, but how can I show that if I own some output and I know this secret key R, no one else can steal the coin, right? There's no more signatures of individual like justifying that some input was spent legitimately. So that's what in our work we did. We looked at this, we defined what it meant to be secure, no one can steal your coins, no one can create money, and we showed that making this discrete logarithm assumption, so assuming this problem is hard in this elliptic curve group that was used, we showed that this is secure. Okay, let's look at what consequences this has. So a transaction now in Mimblewimble is a bunch of inputs that are committed values, outputs that are committed values, some value x, which is defined as sum of the outputs minus sum of the inputs, and then some signature that must be valid under this key x. Now, suppose we have two transactions that are valid, right? So we have one transaction and another one, and they both satisfy this validity predicate. Then what you could do is just merge them together, right? So now you have one big transaction with the inputs of the first and the second transaction, and same on the outputs. And now if you look at the first two, these two equations here, you can just sum them, and then you would get that the sum of all of the outputs minus the sum of all of the inputs is x1 plus x2. So you would get a validity statement for the overall transaction, for this new merged transaction. And you would check the validity of these two signatures. So you can merge together two transactions and get a new validity predicate. And efficiency-wise, if you use something called an aggregate signature scheme, you can even compress these two signatures into one. What you can also do is, not going into too many details, but just mentioning that you can re-randomize stuff, so these values x1 and x2 can actually be re-randomized so that if you only see this merge transaction, you cannot associate inputs to out, you cannot determine which inputs corresponded, which inputs and outputs were coming from the same transaction. So exactly this anonymity property that you can't do in Bitcoin. Okay, so now what I find is the most amazing thing is the following observation. So assume that in the first transaction there was some output that was then spent in the second transaction. That means that this commitment here is the same as there, right? That's the same value because it was spent. Then I claim you can just remove them and still this transaction will remain valid. Why? Because if you remove something from the sum of the outputs and you also remove it from the sum of the inputs, then since these two cancel out, you will not change anything and this equation will still hold for this new reduced set of inputs and outputs. And so what that actually does is exactly that. So we've now cut through an output that was spent in a later transaction and you don't need to store it anymore, and still you can check validity of this transaction. So if you keep doing that, just merging all the transactions of the blockchain together, you will get rid of all the spent outputs, right? You will also get rid of all the inputs. And so all the inputs that are left are these original inputs where the money was created, which are exactly these Coinbase transactions. So in Mimblewimble, the blockchain is basically the cut through of all transactions. And so you have one giant transaction where the outputs are the UTXO set, so all the outputs that haven't been spent yet. Why? Because if an output was spent, it was cut through, and so it was removed. And same thing for the inputs. The only inputs left are the Coinbase transactions, because all the other inputs are outputs of previous transactions, and they were removed using cut-through. Good, so that's a very nice and intriguing concept. So you might wonder, have people actually use this in the real world? Because usually everything that you invent in the blockchain space, someone makes a coin of it and hopes that that's their unique selling point that will make it valuable and them rich. So if you look at the list, the ordered list of cryptocurrencies by value, starting with Bitcoin and Ethereum, if you scroll down a bit, actually quite far, you get to some coins that use this Mimblewimble protocol, worth a few $1 million. So why this original protocol wasn't more widespread? I would argue because the main drawback is that transactions are interactive, meaning that, as you've seen, the receiver of a transaction has to create this commitment so that she's the only one who knows the secret key. And so if you send money to someone, you actually have to talk to that person. Whereas in Bitcoin, you just need to know the address, the public key of the receiver, and you can just make a transaction. So in 2020, David Burkett and Gary Yu, they introduced non-interactive transactions for Mimblewimble. And again, together with Michele Oro, we've analyzed the proposal, we fixed quite a few bugs that it had, and then we formally analyzed it and published this as a paper. And then it actually got some real-world adoption, because since 2022, it is implemented in Litecoin under the name of so-called Mimblewimble extension blocks. And so if you have followed cryptocurrencies for some time, I guess you know what Litecoin is. It was the second big coin after Bitcoin itself, and it's still among the top 20 cryptocurrencies. Good, so that was the first approach to tackling the problem of ever-growing blockchains, reducing it a lot. But now let's go to the second approach called Mina, which wants to go a lot further and proposes a constant size blockchain. So if you're interested in numbers, so Mina is somewhere further down. It's also deployed, has been for a while. Good, so how can you make a blockchain constant size? Seems impossible, right? Because the information has to be there, and with every transaction, as new information has to be propagated. But the idea is I somehow compress everything and make sure that it stays constant. So how do you compress things in cryptography? You commit to stuff. So let's look at this ledger account-based system we had at the beginning again, where the system evolves by such snapshots being published, where you see how much every account owns. And if there's an update, say Alice transfers her fund to Bob, then she authenticates this transfer by including a signature, and so everyone can check that that new block was legitimately derived from the previous block. So these blocks, you can actually create a fingerprint of them called the Merkle hash of a block, and that's also something that's done in Bitcoin. But the idea of Mina is now that instead of publishing the actual blocks, you would only publish these Merkle hash. So that's basically 256 bits viewed as the fingerprint of the block, and it's done in a clever way that allows you to efficiently show that some data was included in that hash. Okay, what's the problem? Of course, if you say your blockchain now is not actual blocks, but only hashes of blocks, the problem is that you can't check whether this new hash here was derived legitimately from the previous hash, right? So what do? You use some more crypto magic and you just prove that that was the case. So you add a proof, in particular a SNARK proof, where SNARK stands for Succinct Non-Interactive Argument of Knowledge, which is some cryptographic tool that allows you to prove the validity of an arbitrary NP statement. And it allows you to do so by just giving you a proof that's a few kilobytes long. So why can you, if you can prove any NP statement, well, obviously, you can also prove that that hash here was derived correctly from that previous hash, because the witness of this NP statement would be these two blocks. You check whether the second block was correctly derived from the first one, and you check whether the two blocks hash to these two values, right? So you can check, if you had that witness, you can check, and the SNARK now allows you to prove this more concisely, even using a lot less information than that witness would be. So how can we make blockchain smaller? Instead of publishing blocks and letting everyone verify that they're correctly derived. You, since the Genesis block, just publish these hashes, these fingerprints of the blocks, and proofs that prove that the new hash was derived correctly. So a hash would be 256 bits, a proof would be some kilobytes, so that's already a huge space saving compared to the 600 gigabytes that you use for Bitcoin. However, these Mina people wanted to go further and make the constant size, right? Here, even if it doesn't grow by a lot, it still grows by a few kilobytes per block. So what can you do? Well, you just give one proof that shows that there is some transition of valid blocks from the Genesis block to the current block. And now your blockchain is just basically these two hash values and this one proof. What do you do if you create the new block? You publish this new hash value. You know that if you have the, as a miner, the old block, you know that you need to show that this was derived correctly from the previous block. So basically you give a SNARK proof that shows that from the Genesis block you went all the way to the current block. So basically the statement that you're proving just consists of these two hash values, right? First hash value of the blockchain and the current one, and you prove that you know a witness, which is this previous proof pi prime, the last block b sub n minus 1, and this new block b sub n. And you show that pi prime was valid for the first hash and the hash of the previous block, that the transition from the previous block to the current block was valid, and that the current block hashes to this value little hn. So what you need for this is actually a specific type of proof system called a recursive SNARK, because the statement that the SNARK proves contains a previous proof and checks validity of that proof. So it's basically applying the SNARK to itself. So the proof statement contains something like verify some statement pi prime. What's the problem with this? The problem is that if, again, avoiding too much detail, if you look at how such SNARK proof systems are actually analyzed and how you show that they are secure, they use an abstraction called the random oracle model, where when you prove security of a SNARK, you idealize certain components, and in particular, these SNARKs, many of them use hash functions, and instead of using the actual hash function, you just pretend that it's a completely random, this hash function is a completely random function, which in reality it's not, but it's an abstraction that allows you to prove something, at least. So one of the systems that is analyzed in this random oracle model is called Plonk, and that's actually the basis for what this Mina protocol uses. The problem, of course, is that the statement verify x prime pi prime, so showing that this inner proof, this previous proof is valid, uses an actual hash function, right? Because the statement cannot instantiate a truly random function. And so it's not clear what security we can still assume of this pi prime. So to conclude, this is yet unpublished work with my PhD student at TU Wien, Marek Sefranek. We showed that for this proof system, you can actually show security without making this random oracle idealizing assumption. And that concludes my talk. Thank you.
Thank you very much for the presentation, Georg. We are now open for questions from the students. You can also speak up if you want. One question in the beginning from my side. You mentioned that like the practical use of Mimblewimble in the example from the green crypto. Do you see for the future an increase of the usage of Mimblewimble for other cryptocurrencies?
I mean, I'm not sure where the development of green is. I know that in the beginning they had this interactive variant of Mimblewimble, where if you transfer money to someone else, you actually have to compute this transaction together. I think they updated it to the non-interactive version. So, I mean, seeing that Litecoin uses it, I think there is a future. I don't know if it goes more towards that direction, or whether the second approach using these SNARKs, which are a lot more powerful, but also less well-studied assumptions on which cryptography is based, so a more high-risk, high-gain approach. Which one of the two will prevail?
Yeah, you mentioned right now SNARKs. Do you see, because we had also the pleasure last year from that presentation, during that year, in that area, do we have any other achievements or improvements during that year in those?
Yeah, so SNARKs is a very active research area, and it's not like it really moved from only being foundational theoretic academic research to industry, and now we have like deployed schemes, and there's been a lot of engineering developments that makes these things really practical, and many applications. Main application scenarios still are blockchains. For example, zk rollups, if anyone has heard of this, where it's a different way of addressing a scalability issue, where you don't change the underlying blockchain, but for example in Ethereum, where you have smart contracts, what you can do is you can just gather a lot of transactions together, do a zero-knowledge succinct proof that what you had is valid, and put that on the blockchain. So now people only have to verify the proof instead of verifying all the individual transactions. And so, yeah, there's been a lot of development in this area.
Yeah. Thanks. Do we have other questions? You can also raise your hand. I see no other question. Otherwise, my last question, or there was something popping up, I see.
I guess you get access to
yeah, sure. Yeah.
The slides, yeah.
Yeah, of course, at the end, everybody get access for the recordings. Those are part of the Wien Informatics webpage. Good. Yeah, one other question regarding energy consumption, energy efficiency. Where do you see also in the future, how big is the potential still for to decrease the energy consumption?
I mean, the notorious energy problems with blockchains, in particular with Bitcoin consuming more energy than whole nation states, is really with this consensus mechanism. So it's kind of an orthogonal problem to what I'm discussing. This is really a topic of Krzysztof's lecture. How can you replace this proof of work in Bitcoin where miners just keep hashing and trying to solve these puzzles by something else. So I think the main approach now, which also Ethereum switched to, is called proof of stake, where it's not the one, the likelihood of mining the next block is not proportional to how much money, how much energy, and thus money, you invested and computing power, but it's about how much you own of the currency, how much you have staked. And so the idea is that people that have currency would also be interested in following the protocol and keeping it alive. And that's very energy efficient. I mean, of course, like compared to AI, completely different scale. Of course, these SNARKs, they're also like complex to compute, especially for complex statements. But that's, I think, the main research direction now is how can we make SNARKs where this prover time decreases, and there's a lot of development going on there.
Great. Thanks. If otherwise there's no further questions.
I would have a question.
Yeah, then please a little bit louder if possible, but go ahead.
Can existing blockchains like Ethereum adapt the space efficient properties you mentioned, so such that the blockchain is not so big anymore?
I mean, that would require a hard fork. I mean, what's done in Ethereum is basically you keep the layer, but then your applications become more space efficient by using this zk rollups. So in that sense, it's a step towards using this SNARK 6 proof technology is already helping making Ethereum take less space because things are compressed into these proofs and not all the data is written into the blockchain.
Thank you.
Welcome.
Thanks, Linus, for the question. Someone else? I think not. So thank you very much for your presentation, Georg. And also for you, Georg, and for the whole audience, I wish you a nice evening. And then looking forward for the next session in 2 weeks, because next Monday it's off. Great. So thank you very much. Bye.
Thanks. Bye.